Hi, thanks, Kelsey. So yeah, I'm going to exactly talk about photonic wavefront sensors for extreme AO systems. So these are probably a slightly different type of wavefront sensor to what you've come across before. So I'm going to talk about two things, and the first is the photonic lantern. And this might be something people aren't very familiar with. What this is a photonic device that takes a multi-mode fiber with a certain number of modes and converts it losslessly into several single mode fibers. So for example, you could have a multi-mode fiber with 19 modes and the photonic lantern will turn it into 19 single mode outputs. And what you have is a direct relationship between the set of modes in the inputs to the distribution of modes at the output. These have been used in various things. In astronomy, they're starting to be used basically to get light into single mode spectrographs, which have all sorts of advantages. And one nice thing you can do is you can put the outputs into a multi-core fiber if you want, and then spectrally disperse it. So what we're going to do here is use it as a wavefront sensor. So the idea is that the modes that are excited in the multi-mode fiber, they're a direct function of the complex amplitude of the light. So the complex amplitude of the PSF, if you're putting this to the focal plane. And therefore the intensities at the single mode outputs are also a function of that. So if you know what that transfer function is, you can work backwards and predict the wavefront. So the trouble is you can't design these things to specify the transfer function at design time because there's small perturbations in manufacture end up having a big effect. But if you could do this, you'd get what you see on the right here. So this is a numerical simulation. On the left is the pupil phase, and I think we've already seen some nice examples like this from Colleen, where the image intensity is, of course, degenerate between the plus, in this case, plus 0.8 radians of astigmatism and minus 0.8 radians. The phase in the focal plane isn't degenerate, as you'd expect. And on the right here, these 19 dots represent the fluxes in the 19 outputs of this single mode, of this photonic lantern. And you can see that the intensities of these 19 intensities are not at all degenerate. It clearly distinguishes between the two. The other nice thing about this, of course, is you can spectrally disperse them as well. So we need to know what this transfer function is. So on the right here, this is another simulation where you can see a set of defocus terms applied in this term on the sort of the top row here. And as you'd expect, the intensity of the PSF is degenerate because of the sign ambiguity, but then the photonic lantern outputs are not. They clearly distinguish between the two focus signs. On the top here, these lines are actually plots of the intensity of the 19 outputs. You only see 4 lines because of the symmetry in this case, so the lines are just overplotted. But what you can see is that over this large range of wavefront errors, so we're going from -2 to +2 radians, we want it to be a high amplitude, low order wavefront sensor. It's non-linear because these are intensities, these are squares. And because you can't specify this accurately at design time, instead we use a deep neural network to learn this transfer function. So we did a laboratory demonstration of this. So the way we do it is we basically inject any modes we like with an SLM into the photonic lantern, and we have some re-imaging things as well. And in this experiment, we just used Zernike modes. We used the first 10 after piston Zernike modes. And what you can see on this bottom panel here, just to give you an idea of scale, this is a back illumination camera. On the left here is the photonic lantern is randomly back illuminated. So we're seeing the multi-mode region, and it's nice because you can see the modes, some superposition of random modes that gives you an idea of the spatial scale. Then in the middle, you can see what the PSF looks like with no aberrations, and here we've applied a bunch of stigmatism and stuff. And the dotted line is the core, so that's like the field of view, if you like. So we basically apply a large combination of wavefront terms randomly drawn, and we, rather than doing one at a time like in conventional response matrix, and this is so we're probing the whole nonlinear space. So in this experiment, we took 60,000 odd measurements, so a minute or something on an AO system. And here's the laboratory results. So we've got the thing to look at first of all is this plot on the right. Each of these columns, 1 through 40, is a randomly chosen measurement that we did. And the black lines show you the value of that coefficient from -1 to plus 0.1 radians for each of these. And the red crosses are the predicted values for all of the measurements. The other colored crosses are just if we use fewer measurements. And on the bottom left here, you can see a panel, the top row, just for 6 randomly chosen wavefronts. The top row is the true values. The middle row is what was predicted. And the bottom row is residual, though notice that this is 10 times smaller, so the residual is extremely small. So we actually get an RMS wavefront error of about 5 times 10 to the -3 pi radians when we have a pi radian. In the last minute, I just want to quickly talk about another photonic wavefront device. This is actually something that is using this is a pupil plane wavefront sensor, but it actually started as a nulling interferometer. So nulling is when you essentially make a coronagraph, but now you do it with interferometry. You destructively interfere the starlight to reveal the planet. This is our chip here, GLINT. And essentially you inject the pupil, each part of the pupil goes into a different waveguide, and then through a series of splitters and photonic couplers where the evanescent fields overlap, you can measure various coherence properties. The nice thing is this goes right down to 0.5 lambda on D. We're talking about wavefront sensors here. And what we found is it actually is a really good wavefront sensor. So what you're seeing on the right here is these are various outputs, and I won't go through what they all are, but what I want you to look at is these two here, N1 and AN1, null one and anti-null one, with the red arrows. Now, what's supposed to happen most of the time is N1 should be dark. This is destructively interfered. And anti-null one is the bright fringe, if you like. But in this, what we're seeing here is this low wind effect happening. If you look carefully, the AN1 and N1 actually swap fluxes every so often. You can just see it happen just there. They swapped. And that's low wind effect. And here is a time series of the same thing. So we should have low light down here with the blue dots, lots of light at the top one, and they swap every so often. And this is because when low wind effect happens, the wavefront sensor actually, because it's at about half the wavelength, actually locks onto the next 2 pi radian fringe over, if you see. So the reason we're so sensitive to it is we're actually directly interfering 2 parts of the pupil. So like Stefan's diagram, he said you need to measure the slopes. Here, we don't care about the slopes. We don't care about a shear or a step in the slopes because we're directly measuring 2 parts. So that's what I wanted to tell you about, and I'll just leave the conclusions up there so there's time for questions. Thanks.
Great. Thank you so much, Barnaby. I think it's probably good that we have a 10-minute discussion coming up after this because I can think of so many questions. It looks like we have a few already on the Slack. One from Olivier who says, can you comment on whether the photonic lantern is expected to be used both for sensing and for science? And if so, what kind of observables can you abstract from the lantern data?
Yeah, great question. So right now for this first demonstration, we've stuck to wavefront sensing, but absolutely, we've actually got a bunch of work going on right now where we're using it for sensing and science. And essentially what we do is we actually double the number of outputs per mode. So if we had, say, 19 input modes, rather than 19 outputs, we would have 38 outputs. And so then you would have you then are measuring the total intensity and the amplitude and the phase of the inputs, rather than assuming the flat amplitude and phase, which we're doing for the wavefront sensing. Then you're getting the full complex electric field of the PSF and the pupil. So then you can actually do image reconstruction. And in fact, one thing we're working on is doing nulling with this, where we actually apply average wavefront with the DM to force some of the outputs to be dark, and they act as a null. So you can null, but now you're nulling rather than having maybe 2 baselines with the sort of fringes on the sky, like you'd be very familiar with, Olivier. Instead, you'd be having vessel modes on the sky, which is a bit counterintuitive. So yes, that is something we're working on.
Cool. And I assume this is something that we can also see more about in the paper you have listed here, right?
Yeah.
Your
so
NORRIS 2020.
Yeah, so those 2 papers, so the top one is actually, it's in press, so it's supposed to be put on the website any day now, but it's also an archive if you can't wait. And then the one with the chip is in the Munras paper. The using it for science observables, that's not published yet. That's actually kind of early days, but yeah, we would love to talk about it with people if they're interested.
I mean, is it something that you've already done simulation work with, or is it something that you've tested already in a lab environment?
Only simulation work, and actually quite like early stages at this stage. We're at the stage where we can get the raw observables, and we've done a bunch of sensitivity sort of calculations to convince ourselves that, because obviously unless you're doing sort of nulling, you're going to be limited by photon noise and all these things.
Of course.
And the nulling you get is quite chromatic right now with these current devices, but we've done sort of the calculation to convince ourselves that you can still get very high contrast things because you're getting all of the telescope pupil, unlike other sort of photonic things where you're just getting little bits of it.
Right. Cool. Very, very cool. Thank you. And again, we have a couple more questions here. Let's see. Jerome says, has the learning process to be repeated for every new AO target spectrum or observing conditions, or is it only specific to your optical design implementation?
The short answer is it should only be specific to the optical design implementation, with the caveat we haven't tested this on Sky properly yet. So, and there's actually one of these is in SkexAO right now. We're working on getting the injection system of that all set up. That's ready to go, and hope the next engineering at the end of the year we'll try that out. But as far as we can tell, based on lab experiments, the only thing it's sensitive to is the physical construction of the lantern. And that's once that's made, that's really sort of locked in place.
Okay. Thank you, Barnaby.